the explanations behind all our demos for this cycle too. In lecture 1, we studied motion in a circle at constant speed. And we looked at it and saw that the x-coordinate and the y-coordinate of this motion looked like harmonic oscillators, with the y-coordinate being 90 degrees out of phase with the x. So that meant that if we could focus on just one of the dimensions, like looking at it on edge, it would look like a harmonic oscillator to us. And sure enough, when we rotate our finger in a vertical circle under the projector lamp, it looked like a harmonic oscillator. The demos of lecture 13. First of all, we were racing, a freewheeling car that was accelerating down, in one dimension. X is the dimension down the ramp. And the freewheeling car, it has a g sine theta acceleration and just starts from rest and goes along a parabola. And then we had a motorized car that went at constant speed. Actually, it was so slow that we had to start it way down almost at the end so that its straight line trajectory would finally hit the bottom at the same time that the freewheeling car did. And sometimes it's hard to draw this, and we get confused about drawing it because we try to start them at the same place in the picture. By the way, if that motorized car were really fast, we actually could start it down here, and sure enough, it could catch up, even though that thing's, starting out accelerating. It could start and catch up with it, and then of course eventually the accelerating guy would catch up later, and because this is going at constant zero acceleration. The second demo, we had a weight hanging by a string, and then of course we pulled on it with another string, and we asked, if we just pulled very gently, which one would break? Well, if we actually just considered, our second law for this mass that's sitting there in the middle, we'd have the tension down, I call it down positive, minus the tension up plus the weight down equals ma, because it's just, there's a very tiny little acceleration as the string is stretching. But this is very small, so that it's really simply T prime is T plus mg. Of course, this tension is bigger than that, and that breaks first. But if we jerk it, then you can think of this acceleration as being bigger, part of the force being eaten up, there's the minus sign, by this mass, and indeed then the T prime could be less initially than the T. The T will be large, break the string below first. Another way of saying this is that, sort of this mass stops the signal, the pull, the effect of this, of the pull from reaching above before the bottom breaks. Lecture 14 demo. We were sliding a car down a ramp, and then it finally slowed down, stopped on a rough rug. It's really very little friction on this ramp and lots of friction on the rug. So let's do it in 2 steps. To start with, we have conservation of energy then, so that we got an increase in kinetic energy of the car at the bottom equal to the change in the negative of the potential energy. So a given height would give me a certain kinetic energy. Then that kinetic energy would disappear as we had negative work from friction. And the negative work from friction is sort of a constant friction force times the distance it goes. So, result. If we had a certain height here, we would get a certain kinetic energy at the bottom from conservation of energy. We'd dissipate all of that with, the friction force. And the height, therefore, would twice the height would give twice the kinetic energy, and that would give twice the distance then that we would go. And If we went half the height, then we'd get half the kinetic energy, and we'd go half the distance. And that was roughly what we saw then in the demo. The two demos in lecture 16. We had elastic collisions. The word elastic should be emphasized here. With one car hitting another car that was at rest. And what we've got is, in elastic collisions, is the kinetic energy is constant and the momentum is constant too. Both of these are conserved. This is one dimension. It's going just in a straight line. So we had this mass, say, little m hitting mass big M. And we knew intuitively what would happen. We knew that if they had the same mass, this guy would just stop and this guy would go forward with the speed that this guy originally had. If this guy were really much lighter, this was like hitting a wall. And when you have an elastic collision with a wall, it just bounces back with equal and opposite speed. And finally, if this were like a wall moving along here, and this was a small particle at rest, then the neat way to think about this was to imagine yourself on top of this ball, riding along with it. You're on the wall, and you see this guy then coming back at you with speed minus v. Your world, everything has been, you've subtracted away the wall's speed. And this guy then would just bounce off of you like a wall and go back at v, but then in the world we're interested in, we got to add back in the velocity of this big wall, and we get 2v for that. Make sure you know how to get those answers from the formulas. Lecture 16's second demo. We had a happy ball and a sad ball. Essentially, the happy ball was material such that it was very elastic, and the sad ball was very inelastic. So if we had a ball coming in and hitting a board that was, perched, balanced vertically, the question was, how could we, knock it over more easily? Well, you knew that with the happy ball, it bounced back off of this heavier board with, almost the speed that it had at the beginning, whereas the sad ball just kind of goes plop, inelastic. Therefore, the change in momentum of the happy ball, in and then back out, the minus signs cancel when you're looking at the final minus the initial, so you get twice the momentum that you had originally. The change in momentum of happy was equal to twice the change in the momentum of the sad. It's a sad, the final momentum was 0. Well, the force is delta P over delta T, and if you think of these collisions occurring at the same time, you could get twice the force with the happy, and the board would tend to be knocked over more easily with the happy than with the sad. And that's what we saw.